Bridges are visible, tunnels are invisible, and that's what makes this one terrifyingly impressive. Beneath one of China's busiest straits, engineers are drilling a 16.18-kilometer rail tunnel, with more than 11 kilometers of it underwater. Linking the mainland to the island cluster at speeds up to 250 kilometers per hour. It is not just a shortcut. It is a new benchmark, replacing ferries with high-speed precision, where a single mistake could mean disaster. The real warning to the West is not in secrecy. It is that China is quietly changing what is possible underground. But the stakes run deeper than most realize. How do you dig beneath chaos and deliver the impossible? Every morning, ferries crowd the waters between Ningbo and Zhoushan, shuttling commuters, students, and truckloads of goods across the strait. For decades, this crossing has been a bottleneck, subject to tides, fog, and the constant threat of typhoons. Trucks line up at the docks, waiting for space on the next boat. Families plan their travel around unpredictable schedules. For the people of Zhoushan, the sea has always been both a lifeline and a barrier. With the tunnel, that barrier begins to dissolve. The new rail link promises to shrink the journey from over an hour and a half, sometimes far longer in rough weather, to just half an hour. For a worker living on Zhoushan and employed in Ningbo's factories, this means more time at home and less spent waiting for a ferry that may or may not arrive on time. For a student, it means access to universities and opportunities on the mainland without uprooting their life. The tunnel doesn't just move people faster, it redraws the map of daily life across the islands and the coast. This project is a straightforward shortcut that changes how daily commutes and regional travel work. Zhoushan's role as the world's busiest port by cargo volume adds another dimension. Freight that once crawled across bridges or waited at ferry terminals will now flow directly onto high-speed trains, joining the arteries of China's national rail network. The result is a tighter web of commerce where seafood from island fisheries, manufactured goods, and critical supplies move seamlessly between ships and rail cars. Businesses on both sides of the strait can plan, expand, and hire with a new sense of certainty. This isn't just about shaving minutes off a timetable. The tunnel is designed to bring the islands into the economic core of eastern China. It links remote communities to jobs, healthcare, and markets that once felt out of reach. For the region's logistics industry, it means fewer weather delays and lower transportation costs. For local governments, it's a chance to attract investment and talent that might have looked elsewhere. The promise of integration also comes with new questions. As the tunnel prepares to open, old routines fade. Ferry operators, long the gatekeepers of the strait, face an uncertain future. The rhythm of island life will change, as will the pressure on local infrastructure and resources. The payoff is real, but so are the risks that come with building beneath one of the busiest and most unpredictable waterways in China. The next challenge lies not in the promise of speed, but in the realities of the sea and the shifting ground below. Beneath the crowded surface of the Jintang Channel, a different world waits, shaped by relentless pressure, shifting geology, and the ceaseless movement of ships overhead. This is not a gentle seabed. At its deepest, the tunnel will lie nearly 78 meters below the waterline, buried in a zone where the weight of the sea above pushes down with a force that would crush a submarine hull in seconds. Every meter deeper multiplies the risk as hydrostatic pressure climbs and the margin for error disappears. The channel itself is a living obstacle. Cargo vessels, tankers, and fishing fleets cross these waters day and night, feeding the world's busiest port just a few kilometers away. There is no pause in the traffic. The tunnel route must pass beneath this marine highway without disturbing navigation, threading a path through a gauntlet of oil pipelines, seawalls, and dock foundations. Above, radar screens track hundreds of ships at once. Below, engineers must predict every movement of the ground. The geology under the channel is a patchwork of contradictions. In some stretches, the tunnel faces soft, silty clay, so unstable it shifts under its own weight like wet rice cake. In others, it slams into hard volcanic tuff, dense enough to spark against steel. The transition between these layers can happen in the space of a few meters, forcing the tunnel boring machines to adapt instantly, or risk getting stuck, flooding, or worse. 28 different strata lie in the tunnel's path, each with its own hazards. Some zones are riddled with ancient channels that leak water at high pressure. Others hide pockets of gas or fractured rock that can collapse without warning. Every advance of the cutter head sends sensors into overdrive, measuring ground movement, water inflow, and the stress on the machine's shield. The margin for error is razor thin. Even a minor miscalculation could send water surging into the tunnel or cause the ground above to settle, disrupting shipping lanes and threatening the safety of both workers and vessels. The tunnel boring machines crawl forward in this environment, their progress measured in centimeters, not kilometers. In this place, the tunnel is not just a line drawn on a map. It is a contest with the sea, the ground, and the unpredictable forces that rule the space between. The environment here is not passive. It pushes back at every turn, demanding precision and vigilance. This is the test that will define whether the promise of a seamless mainland-island connection can survive the realities of the channel below. Deep beneath the Jintang Channel, the heart of this project beats with steel and hydraulics. Tunnel boring machines, each longer than a city block, grind forward against the pressure of the sea above and the unpredictable ground below. These are not off-the-shelf machines. The tunnel boring machines driving this tunnel are named Yongzhou and Dinghai. They were built to order, their cutter heads bristling with hundreds of custom-designed discs. Each disc is chosen for a reason. Some are built for slicing through soft, sticky clay that clings like wet dough, while others are forged to shatter volcanic rock hard enough to spark against steel. The cutter head itself is a rotating wall of teeth and sensors, monitoring wear and alerting crews the moment a disc needs to be swapped. Swapping a disc in this environment is not a simple task. The cutter head sits under immense pressure, with the sea pressing in from all sides. To keep the tunnel face stable, the machine uses a slurry shield system, a closed loop that pumps a thick engineered mud to the front, balancing water pressure and carrying away crushed rock. This slurry must be carefully managed. Too little pressure and water could burst in, flooding the machine. Too much pressure, and the ground above could heave, disturbing the busy shipping lanes overhead. Operators monitor gauges and flow rates in real time, adjusting valves and pumps to keep the balance perfect. Spoil, which is the broken rock and soil, travels back through pipelines, snaking out of the tunnel to barges waiting at the port. Every advance is measured in precise steps. As the machine chews forward, it pauses for crews to install giant concrete rings, precast segments that line the tunnel and lock together like pieces of an enormous puzzle. These segments arrive just in time, delivered from factories by barge and truck, lifted by overhead cranes, and slotted into place by crews working in shifts around the clock. The logistics are relentless. Each ring must be perfectly aligned, not just for the train tracks that will come later, but to keep the tunnel watertight and stable as the machine pushes deeper. If a segment is even slightly off, the entire operation slows and the risk of leaks or settlement grows. Inside the tunnel boring machine, the atmosphere is tense but methodical. Operators sit in command cabins surrounded by screens, tracking the position of the cutter head, the pressure at the face, the temperature of the motors, and the flow of slurry. Maintenance crews stand ready to enter the pressurized chamber when a cutter needs replacement, donning special suits and working against the clock. Each intervention is planned and rehearsed because any mistake could let in water or destabilize the ground. The tunnel is a living system, and every part, cutter head, slurry loop, segment ring, logistics chain, must work in harmony. This is where customization matters most. The machines are tailored for the Jintang Channel's unique geology, built to handle sudden transitions from soft silt to fractured rock, and equipped with intelligent monitoring that can sense trouble before it becomes disaster. For the crews inside, every meter gained is a small victory against the sea. The risks are real, but so is the sense of purpose. Each shift brings them closer to the moment when the two machines will meet deep below the strait, in a feat of precision few have ever attempted. Deep inside the tunnel, the difference between triumph and disaster is measured in millimeters. The two giant tunnel boring machines, Yangzhou driving from Ningbo, Dinghai from Zhoushan, are not simply digging toward each other. They are locked in a high-stakes exercise in alignment, where the margin for error is smaller than the width of a finger. Every meter advanced under the Jintang Channel brings the machines closer to a meeting point set with a tolerance of just 2 centimeters. That level of precision, under nearly 80 meters of seawater and through 28 unpredictable layers of rock and silt, is not a matter of luck. It is the product of a continuous feedback loop, an invisible web of measurements, corrections, and real-time decisions that starts long before the machines even touch the ground. The backbone of this operation is a suite of advanced surveying and navigation systems. Laser theodolites, inertial sensors, and digital control networks form a chain of reference points from the surface, down the shafts, and deep into the tunnel itself. Each segment of the tunnel is mapped and checked, then checked again. As the cutter head pushes forward, sensors track its position in 3 dimensions, correcting for drift, vibration, and the subtle shifts of the ground. Any deviation is flagged instantly. Operators in the command room watch a constant stream of data, angles, distances, and pressure readings, comparing the live position of the machine against a digital model of the planned route. If the machine strays even a few millimeters, automated controls make micro-adjustments, steering the cutter head back on course. Every ring of concrete installed behind the machine is surveyed, its position logged and compared to the design, ensuring that the tunnel remains true from end to end. This is not just about high-tech sensors or clever software. It is about discipline and routine. Before each shift, crews calibrate their instruments, running checks with laser targets and reference prisms. Survey teams move in behind the machine, setting up temporary benchmarks and cross-checking measurements by hand. The process repeats, hour after hour, day after day, until the tunnel becomes a single continuous line, straight, level, and true. When the two machines close in on each other, the tension in the command room is palpable. On the screens, a simple diagram shows 2 arrows converging on a tiny circle, the target zone where the cutter heads must meet. As the distance narrows, the margin for error shrinks. In the final meters, progress slows to a crawl. Operators scrutinize every data point, ready to halt the advance if the numbers slip outside the tightest tolerances. The breakthrough, when it comes, is almost anticlimactic. After months of calculation, drilling, and adjustment, the two machines finally meet beneath the seabed. The measured deviation is less than 2 centimeters, verified by independent survey teams. In some reports, the vertical error is just 2 millimeters, with no measurable horizontal offset at all. For the engineers, this is the proof that extreme accuracy is not only possible, but repeatable, even in one of the world's most hostile construction environments. The achievement is not a single moment, but the sum of thousands of corrections, a silent choreography of people and machines working in perfect alignment. In the command room, the celebration is quiet, just a new entry in the logbook, and the knowledge that the tunnel's invisible backbone holds true from shore to shore. Inside the Jintang Tunnel project, the real story is about orchestration on a scale that few countries can match. Every concrete segment lining the tunnel is cast in precision-controlled factories, then shipped just in time across port facilities that already handle more cargo than anywhere else on Earth. These segments do not wait in stockpiles. They move from mold to barge to crane to tunnel face, tracked by digital systems that monitor every step. The factories run on schedules set months in advance, adjusting output to match the tunnel's daily progress. If the TBM advances faster one week, the factory ramps up. If geology slows work, shipments pause automatically. This rhythm, connecting manufacturing lines to port logistics and on-site assembly, is what lets crews keep pushing forward without costly delays. Quality is never left to chance. Each ring segment is checked for dimensions, strength, and water tightness before it even leaves the factory floor. Barcode scanners log every piece, linking it to a digital record that follows it underground. If a problem ever surfaces, for example, a micro crack or a misaligned joint, engineers can trace the segment's entire history, from the batch of concrete to the day it was poured. This level of traceability is standard here, not an exception. It is the backbone of a system where mistakes are caught early, and corrections ripple through the supply chain instantly. The warning to the world is not about the tunnel's depth or the speed of the trains. It is about the machinery behind the scenes, the factories, ports, and logistics teams moving in lockstep, guided by engineers who treat the project as a living system. This is not just construction, it is industrial choreography. The lesson is clear. When every part of the process is integrated and responsive, the limits of what can be built begin to shift. Every undersea mega project leaves a mark, and the Jintong Tunnel is no exception. Excavation beneath the channel stirs up layers of sediment that have been settled for centuries. As the tunnel boring machines advance, the slurry shield method keeps water at bay, but also risks releasing plumes of fine particles into the surrounding sea. These clouds can drift with the currents, sometimes spreading beyond the immediate construction zone. Fisheries and marine habitats, already under pressure from shipping and port activity, face new uncertainty as the balance shifts. Environmental monitors track water quality and sediment movement, but the true impact on local ecosystems may not be clear for years. On land, the story is just as complicated. Construction sites near docks and neighborhoods bring noise, dust, and traffic. Temporary land use for shafts and segment yards reshapes familiar spaces, while the constant flow of materials and workers strains local infrastructure. Some disruptions fade quickly, others linger, changing the rhythm of daily life. Yet for many, the promise of faster connections and new opportunities outweighs the inconvenience. Communities adapt, but the disruption is real. Timelines for a project of this scale are always in motion. Official targets put tunnel breakthrough by the end of 2026 and full railway operation by 2028, but progress depends on geology, weather, and the pace of assembly. Some segments may open sooner, others later. Status tags now read under construction and target from 2026 to 2028, source dependent, a reminder that even the best planned schedules must adapt to the realities underground. Beyond the immediate horizon, some commentators look to the Jintang Tunnel as a sign of what is possible. They speculate about even longer crossings, such as a future link beneath the Taiwan Strait, and they point to Jintong as proof that the technical barriers are shrinking. This is speculation. For now, the tunnel beneath the Jintong Channel is a feat in its own right, and any talk of new frontiers belongs to a different chapter. Today, the world watches as China sets a new benchmark for undersea engineering, achieving sub-millimeter tunnel boring machine precision beneath 78 meters of seawater. This isn't just infrastructure. It's an industrial signal sent in real time. As mega projects grow bolder, the line between ambition and capability keeps shifting. In the end, the future belongs to those who can build it, no matter what lies beneath. What do you think this means for global innovation?